Good morning, everyone. Today's speaker is Sabyasachi Basu. He was an undergraduate student at IISc from 2015 to 2019. After that, he is now a PhD student at UCSC with Professor Sheshadri Pomandu. His primary research interests are in graph decomposition problems and sublinear algorithms. And today he will speak to us about covering a graph with 10 subgraphs, theory and practice. Over to Shobho.
Thanks, Adit. Okay. Is there? Okay, is the password just going to be there? Or? Yeah. Cool. Thanks for the introduction. Thanks for having me. Yeah. So, yes, yeah. As Adit mentioned, I work at UC Santa Cruz. I'm hoping to graduate by this time next year. Primarily, I work on graph algorithms, and the focus I have bridging theory with practice. And the unifying theme often ends up being graph decompositions in various shapes and forms. So I have some work on property testing in bounded degree graphs. Some of my collaborators have given a talk on that here. There's some other recent work I've done on sublinear algorithms for real world tasks like spots and stuff. And the other is finding dense subgraphs in your graph. And I've also done some problem embeddings and recommendation and such tasks, but today I'll be focusing on this problem subgraphs, in particular one's very specific variant of that, where I want to cover as much of the graph as I can with dense subgraphs. And throughout this talk, when I say dense, there are various notions of density, but when I say dense, or say, I say edge. Is this visible? Bigger? Okay. I'm in the subgraph H. I look at the number of H divided by the maximum possible number of edges inside H. So essentially how close your graph is per clique. I'll also be talking about triangle density, which will refer to the same quantity, except this will be number of triangles and this will be essentially maximum possible number of triangles. Does that make sense? The setup? I think it's good to clarify because there's another very well-known notion of density, but this is what we'll be focusing on today. And I'll tell you why we care about this. So today's talk is primarily going to be based on this paper, which is triadic decompositions of real-world networks. It appeared on the Science Journal on Mathematics of Data Science, literally, I think 2 weeks ago. So this goes to our archive, I think, but if you go to the journal's website, you'll find the full paper. And if we get time towards the end, it's a bit of a long talk. I will also cover some material from the second paper, which is covering a graph with dense subgraph families via triangle with sets. Yeah, this one was with a bunch of people at Amazon and Daniel, who's a co-student with Session Me. Okay, so the goal, hopefully by the end of this talk, I'll show you how you can take a graph, which looks like this. This is an adjacency matrix from a Facebook network. It's a small section of that network. I will give you an algorithm to take this and go to this. And this turns out often quite hard to do in real networks. And I'll show you what challenges people are faced with and which of those we can overcome. So goal, use dense subgraphs to cover a graph, covered in a very loose sense. So setup. So this problem of finding dense subgraph can be studied in various forms. I like to think of it as kind of a spectrum, where at one end you have this small motif counting problem, where I give you like, okay, look at all possible motifs that you can find across, say, 5 vertices, 6 vertices, 10 vertices, something like that. So it still could be a fairly large number of possible motifs, but it's an explicit bounded problem. What is a motif? Oh, a motif is essentially you take a subgraph and you take like an isomorphic different possible copies of induced subgraphs. So for example, a motif on 5 graphs 5 vertices is, say, the complete graph on 5 vertices, the cycle on 5 vertices, a star, so different variants. So all of these are different motifs. And there's a rich body of work that cares about counting these motifs, how you can study this, what is the hardness for these things, and so on. There's other work which is quite good at extracting dense subgraphs in a slightly different sense, usually, where these dense subgraphs are of size like a constant size of the graph itself. I will come to some details about that later on, but the property we care about is the stuff in between, where it's not particularly tiny graphs, but also not these huge subgraphs. And there doesn't seem to be a lot of work doing that. And the closest fit we found was this series of methods called community detection in real-world graphs or networks. This is a field that has received a lot of attention across different communities, physics, applied math, CS, and so on, and it's heavily used by practitioners in various different fields. A lot of people in biology use these methods, sociology, and even like social sciences. Fields further and further away from the quantitative sciences as we like to think of. But the question that occurs when you fit such a problem is what exactly is a community? And if you ask one person, they'll give you an answer. You ask the next person, they'll say, okay, no, that's not an answer I'm happy with. They'll give you a completely different answer. And it becomes a hard problem to even like formalize. So I'll not spend time giving you what a community is. I'll give you some descriptive methods and tell you that, okay, maybe this makes sense that if I do this, what is left, I'm left with is a community. Does that make sense? Okay. So let's take one thing. It's probably reasonable, I think, to say that a community is something which is kind of, you can separate the community from the rest of your network by a small piece. And you cut this, and there's a small cut, and it's kind of weakly cut to the connected to the rest of the network. So you say that this is a distinct community of its own. And there are various variants of this min cut-like statement. And this is not a terrible start, but this, first of all, this will fail if your community is overlapping. And this is a problem that appears a lot in real life. For example, like if you look at a product catalog on e-commerce, you'd say you look at diapers, which is, for some reason in e-commerce, it's very popular. I've seen people give this example a lot. This will be in multiple different, if you look at the taxonomy tree, it'll be in health and hygiene, it'll be in families. And it'll be in a lot more than just that. So anything that does this will never find the right communities here because there's no actual min cuts like that in your graph. And even if there is a min cut, like there is a nice separator, this phenomenon, just measuring the min cut, is not usually a good idea because there's a lot of edge cases everywhere which can completely skew your output, and turns out it doesn't work well in practice. So the natural, perhaps, extension to that is say that, okay, let's maybe also see what the thing I've cut out looks like. And that's where we actually get the sparse cuts, which essentially look at low conductance cuts. So you don't just look at the value of the cut itself, but you also look at the volume inside the cut community. And theory people, especially, we love this because it has nice ties to the spectrum of the graph. The very celebrated Chigorin inequality is perhaps one of the cornerstones of spectral graph theory. And there's been a lot of seminal theory research continues going on, all very cool stuff I personally like very much as well. The issue with this is fundamentally a binary procedure. It is somewhat understood when you have a finite number of k blocks, but to the best of my knowledge, there is not a lot of work on understanding if you just say that, okay, there's a lot of maybe ON number of communities in your graph. Sorry? So fundamentally, the sparse cut research that at least I know of, it cares about dividing your graph into two pieces, or at most a constant number of k pieces. And in many cases, you might actually have the number of these communities, loosely speaking, grow as the size of the graph as well. And in that case, I don't think the theory is there yet. I don't know if people have studied that, but to the best of my knowledge, people have not. And the spectral gap itself is kind of unstable for real-world graphs. Like you can add a little bit of noise to your graph, and the spectral gap gets completely destroyed and modified heavily. And however, it still is the building block of a lot of. Okay, yeah. The other thing is it still need some form of a clear separator. So for this example, the conductance-based methods will not actually give you these two separate families. It does still, however, form the basis of a lot of popular algorithms. And there is value in looking at this. And personally, we like it because this nice tie to the spectrum is something we found very interesting mathematically. And remind me in a little bit, I'll show you that we can also get some notion of a connection with the spectrum of the graph, but we can get over some of these issues. Any issues so far? Any questions? Okay. So if you don't actually have a clean cut separator, then you can say that, okay, yeah, let me not look for these clean cuts because yeah.
So does the conductance methods do better on sets like diapers?
Depends on how overlapping your communities are. In some cases, they can give you somewhat decent results, but I actually have a few experiments on this as well. What happens is that okay, since I'm here anyway, I'll say this. The spectral cut methods, typically they ask you for the number of pieces. And essentially, if you change the number of pieces, your output varies a lot. And fundamentally, it's not a very good goal, I think, because in an unknown network, you do not know what the right number of pieces is. So what you will often get is you ask for, say, K50, and you get a bunch of things which are like, oh yeah, singleton, edge, small motifs, blah, 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 and then there's one big piece. So there's places where they do work well, but there's also other places where they don't. Does that answer the question? Good. Any more questions? That's actually a very important point. And I think I have slides on experimental results on that later. Okay. If there's no more questions, then okay. So both of these methods I've highlighted are not exhaustive. There's a lot of literature that goes into looking at cut-based community detection methods. But yeah.
I understand what's the connection between the graph and these overlapping communities.
Oh, okay. So these, for example, these can be modeled as graphs in like. So you can typically look at like similarity graphs. So a node would be an item in the catalog, and essentially say toothbrush and toothpaste. These go well together. So you put an edge between them because they're quite similar. Sorry, that's probably something I should have clarified. No, family is a big cluster of different nodes. Diaper is a node inside. Yes, exactly. So maybe. Yeah, exactly. Sorry, maybe that was not clear. Does that, if anyone else answered that, any more questions to that end? That's a good question. I should have clarified. But typically, will look at these things as graph, and they'll actually try to build very complicated like knowledge graph like things on top of that. But you can look at each item in the catalog as a node, and you can get different kinds of similarity graphs on that. The communities are often, in fact, overlapping. In our case, yet no. But what we can do in this case is most likely, if you have heavily overlapping communities, most things will give you that as a single output. What we can do is, okay, we are cutting off part of your thing, but the rest we can probably still output as a distinct one. So that's actually a question I get quite often, and hopefully if you ask me in the next few months, I'll actually have concrete results on that. It's something I'm working on right now. Yeah, we also have some work on that. It's on the way, but it's not a full paper yet, which is why I don't talk about it. Okay, yeah, great questions. Any more questions? So in the absence of a clean cut or separator, what can you do? Does anyone have any guesses? How can I find these dense subgraphs? Any guesses? Like what's a possible method you could use? So Yeah, exactly. So that's exactly my next slide. You can take a density-based objective and say that let me look at how I can maximize this objective, and you have a density objective like this. Very early on, when I was just starting to work on this problem, someone asked me, why can't we just do this? So are people familiar with Charik's scaling algorithm? Okay. So it's a very simple algorithm which gives you a true approximation to this output. It will give you a single dense graph though. It doesn't give you a full thing. So what you do is you basically iteratively remove the lowest degree vertices. And you can show that this will give you the maximum in this series will be a true approximation. This was first proposed, I think, by Ashahiro, but Charikar did the actual worst case analysis. It's known more colloquially as Charikar scaling algorithm. It's very fast. It takes linear time because you just do one iteration. And so someone asked me, why not just take this? You remove your densest subgraph from your and iterate that all over. So let's iterate this procedure. You remove it and you iterate that. Does anyone see what could go wrong here? Okay, so maybe I'll give the answer. Okay, so it's kind of a weird objective because suppose you have two. This is something I think about and wonder if there's a way around this. But if you have two disjoint sub don't talk to each other at all, which have the same objective, then their union is also going to have the same value, which is kind of a weird thing. Like if you have multiple things, like all of them being degenerate and their union being degenerate, any arbitrary set of unions being degenerate, it's kind of a weird thing, at least to me, from this application point of view. Okay. The other thing is that this metric is just average degree, which means that if you take a large sparse graph, maybe of size, say 10,000, and you just have average degree 50, that is going to be better than any small complete graph on, say, 20 or 30 vertices because the average degree is just higher. So again, the metric I care about was that, and it performs poorly on this. You can try it on real graphs. It's actually very simple to code up, and it does do that. We have seen that if iterated, it prefers these larger, kind of sparser with that metric in mind, subgraphs to the things we would like to think about. Does it make sense? Yeah.
So you can always some notion of centrality.
That's actually, so I don't know if people have explicitly studied that centrality notion, but that's not a bad idea. In fact, what I'll show you is that not in this setting, but the things we have can perhaps be thought of as something like that. Like essentially, you can measure how far your different things are from some seed vertex and try to maximize closeness in terms of that. Is that what you had in mind? There's so one thing you so okay, maybe we'll talk about that later on if we get there, because I talk about it briefly at the very end, and given time, I still haven't set up the problem. So getting around these issues for the optimization things, a common thing to do is put constraints on the size of these subgraphs. And turns out these are well-known difficult problems. I'm not an approximation algorithms person, so I am not completely up to date on what is the latest. But these approximation algorithms typically are not that great, to the best of my knowledge. And I think there's three commonly known variants, which is densest exactly k subgraph, densest at most k subgraph, and densest at least k subgraph, which I think at least k is slightly better done. I think that we have like constant approximation algorithms, but the rest I think are still, I mean, these are inapproximable to the best of my knowledge. I think at least k is the easy one. I think there's a 2 approximation for that. The rest I think are inapproximable. So that edge density thing over there, it's a slightly weird quantity because basically you take any edge and that's maximum for that. So there's variants of that which are called the optimal quasi-clique thing. It's essentially you measure how far your graph is from a clique and you normalize it with some size thing. Those are also hard. There's not nearly as much work on that. But my point all of this NP hard, like this is for a single dense subgraph. It gives you a decomposition to begin with. So these optimization things, we spend time getting around hard cases, and turns out in real life this becomes not very practically usable. If you want to look at the, more up-to-date literature, this survey actually does a great job. It's just come out in one of the ACM surveys. So yeah. Okay, this is hardly an exhaustive list, and if you just look up community reaction, there's been 74 million, 7.4 million papers on that. 2024 alone, there's been 24,000 papers. This is like, this beats graph neural networks even. So I think the only thing I found which had more papers was attention or large language models. And there's a lot of popular types of these algorithms. I'll skip over the exact types, but may take my word for it for now that there are issues with a lot of these methods. So the challenges is, first of all, there's no consensus on what's right. A good theory doesn't scale well for the settings that are useful in real life. And the explicit optimization frameworks have a bunch of other issues, like it's not only expensive, it's also slightly doesn't look at the right thing. And methods that work well in practice have other drawbacks. So finally, at 23 minutes, I can give you what we do. Okay. So our aim is to get good theory for dense subgraph discovery usable in real life. First thing we do is we give you a criterion to determine the existence of dense subgraphs. This is a new criterion. This was not known before this, at least in this form. And I think the cool thing about it is it relates triangle density to the spectrum of the graph. And triangles are, so the way we approach this is we know something is true in real world graphs. We try to take that property. Real networks have a lot of triangles, and we translate that into a spectral quantity. We give a very efficient algorithm to find them. I will link you to code to this, which is not just, I mean, theoretically, it's quite efficient, but also in real life, you can run it on your local laptop on a 100 million edge graph, and it will give you a decomposition in half an hour. We also give a new goodness metric, which I gave you a bunch of metrics. We will give you a new goodness metric. We don't think of it as an optimization problem, but maybe someone here can get an optimization problem which relates this in the more classical approximation algorithm setting. Okay, so I'll give you a rough main theorem, which is we define a metric f for the graph. When f has values in some range, we say that G, the graph, can decompose into many subgraphs such that each is internally dense. What I'll do over the rest of the talk is unpack first this statement, then that what nicely means, and what this notion of internal density is. Any questions so far? I think it's a good place to take a break and ask questions if you have. No? Okay. I will admit that this is very heavily inspired by some old work my advisor Sesh had with Tim Roughgarden and one of his students, Rishi Gupta. This came in ITCS in ICTS. Wait, is it ICTS or ITCS? ITCS, yeah, sorry. So, sorry, ITCS is across ICTS. Okay, never mind. You know what I'm talking about. So that paper cares about decompositions of similar graphs, but they care about preserving the total triangle count. This is an inspiration, and we provide kind of a spectral interpretation of what they do. But their algorithm fundamentally had a flawed goal. I will show you what that flawed goal is. I will show you how we can get around this. And I'll show you that getting around that flawed goal will actually solve a mathematical issue for us as well. The algorithm does not go through identically, unfortunately, but that is it kind of solves a lot of issues for us. As in the algorithm, like they propose an algorithm. Our algorithm is not identical to theirs. We have to do things a little more carefully. It's similar, but it's not the same. And that little difference turns out it leads to a lot more nuance required, but it also solves a lot of issues. Okay, so what issues? I said solves a lot of issues. What issues? Our outputs are disjoint, which is a question that Rahul asked. Like our outputs are disjoint, but they do not need to be like this fundamentally well-separated thing. Our outputs cannot be arbitrarily large. If you look at the optimization frameworks, you'll see that they output large, huge subgraphs. In the second paper, there's numbers on that. And I think a very useful thing from an application perspective is that we don't need to give you a prescribed number of pieces and tell you there are this many communities. It'll find out so many dense pieces and just give you those dense pieces. So, any questions? And we guarantee internal density, which is not particularly common among other methods. And we do this in terms of both triangles and edges. So before I go into the details, I'll quickly first go through, okay, yeah, it also is robust in a sense, but I'll first talk about what I mean by this internal density thing. So why internal density? And turns out that this notion, so I think there's many different notions of communities, but I think a commonly recurring thing is that almost everyone seems to agree communities have stronger inties than out. There might not be a clean separator, but things are more densely inside than with the rest of the world. And so essentially anywhere that communities are a good proxy, turns out like looking for density-based things give you good results. So if you go on YouTube and you look at co-watched videos, you can get a cluster of co-watched videos by looking for internal density. You can find co-bought items on an e-commerce catalog using this. If you look at biological networks, functional protein units have very high internal density. They form a single unit and are internally very well connected. And in financial networks, people use these as primitives to find for fraud detection and anomaly detection procedures. There's a very, very good survey on this as well. I wish I could go through this, but unfortunately there was a tutorial, so I cannot. Fantastic applications with actually fleshed out examples. In the ML age, people typically say, okay, let me take an embedding of your graph and put it in some low dimensional space, and let me find some nearest neighbor-like thing. I'll give you an anecdotal example. The slides are courtesy of my advisor. It is an anecdote that you can poke holes into what I'm saying systematically, but these are real life things that have happened, and you can try these out yourselves. So I'll take a DVLP citation network. So each vertex is a paper, edges are when papers cite each other. So typically this is a directed graph, but we'll consider it to be undirected by just removing the direction. And we'll get personalized PageRank clusters from this. So are people familiar with what personalized PageRank is? So it's kind of a diffusion procedure. So PageRank is the procedure that Google used to use back in the day for recommending similar websites. Personalized PageRank is a modified version of this. It's a random walk-based diffusion procedure. And I'm not going to go into details of that, but again, take my word for it that it's very well established as a method to find similar things in a graph. So we took this and we picked this paper which said on privacy preserving HCI issues. And we looked at what the PPR cluster would look like. And the red ones are not actually similar relevant papers, but the rest are all relevant. And you can see that these are internally quite dense. Happy? Let me do another thing. Let me actually take a dimension, an SVD of the graph and get a 100-dimensional embedding. So each paper has a 100-dimensional embedding. I turn this embedding into a new graph by adding probabilities with just the truncated dot product. And then on this new graph G prime, I run the PPR cluster. This is what it looks like in your real graph. So I took some graph, I took an embedding, I created a new graph from that. And typically you would hope that the embedding actually preserves this notion of similarity. But if I run PPR on that graph, the output thing, if it correlates to the original graph, is actually an independent set. This is an anecdote, it's an example. It is cherry-picked, but I'm putting this out here because this is common. It may not be an independent set, but it's actually often. So the output is, so PPR, you would hope that the PPR clusters I showed you actually are good proxies for internal density in the previous slide. So this was the original cluster. It's a cluster in your original graph used. So I found a cluster using PPR. Now I take an embedding of the graph and I make a similarity graph out of the embedding. I run the same clustering procedure. Turns out the cluster, that cluster is actually not a particularly good dense community in your graph. There's a reason for this. Not everything is terrible, but low dimension reductions are tricky. And wait, this is mainly because the vertex we use, the metrics we use to study these are often flawed. We care about things like ROC, area under the curve, and stuff like that, where you essentially care about the net thing. But if you look at, just switch this to a vertex-centric measure. This is ROC curve. This is, so VCMPR, think of it as you look at per vertex and you try to see how many of these vertices have good output. That decays a lot faster, even for the methods that do nearly perfect, like close to perfect in the ROC curve. Our metrics are flawed. We are training embeddings using metrics that actually do not give you good outputs, because if you look at per vertex, there's usually a heavy tail and that doesn't pan out well. These are improving day by day, but there is value in looking at internal density, and these are things that are not trivial to find. Yeah. It is looking at the mixing of that, but good question. I'm not exactly sure, but I also don't know why the embeddings are not doing that badly either. Because given the size of the graph, 128 dimensions, 100 dimensions is not terrible. You would expect that there is sufficient stuff being preserved. Again, this is a cherry pick bad example, but usually if we look at the vertex centric measures, it turns out to be like overall things are not great. This is very recent. This is like 2 months ago. So this is a great question to ask. I do not know why that happens. I have done this in other settings and the same issues happen. I have done it for a more recommendation-based setting and we have the same issue. In fact, that's why real-world recommendations are often bad, because you have a long tail of users for whom you do not have a lot of information. And for them, recommendations are typically poor. Okay, I'm at half an hour. I should really move on. Sorry. The other thing is our outputs cannot be arbitrarily large. Turns out this is actually a common issue across community detection methods. But again, we have these three things. So that ON things I meant the densest subgraph variance. And turns out that the community detection methods also have these issues. So this is a method called modularity maximization. This is an extremely popular method. I'll not go into the definition unless you want me to. Maybe offline I can show you what the definition is. But it's a very popular method, and for a lot of tasks, it does work well. Kind of think of it as it's kind of measuring your distance from a random graph, given that same degree distribution. Like you'd say that, okay, this vertex has this degree and so on. Given this thing, you're trying to see how far your given graph is from a random graph with that degree distribution. And what happens is that often these methods, they will merge a lot of actual clusters and give you much larger outputs. Turns out this is a well-known thing. If you're familiar with some community detection algorithms, there's something known as the Louvain algorithm. It's fantastic, works really well in practice in many cases, and there's also improvements to that. These methods fundamentally have this problem. This is known as the resolution limit. It's a well-studied issue. A lot of community detection methods cannot actually do well when things get small. They'll merge a lot of things, or even if things are a bit like non-uniform in size, the communities, they'll try to either break them into small pieces. Like they want some notion of niceness across your output. What we say, we can give outputs which actually are reasonably sized. In modularity, you can like maximization, you can actually get like much larger results. So this again, this is just a pitch that having that size bound on the output is useful. Okay, so it's enough for motivation, I think, and hopefully people are grounded in why the things I'm trying to show are useful. Any questions about this? No, the size that we pick actually will depend on the number of roughly we'll have some notion of a seed vertex, and we'll look at the degree of that seed vertex, and we'll give you an output which is not much bigger than the degree. That's a good question. We'll get to that in a little bit. Come in. Kind of. Again, we do not look at it as a centrality measure, but I suspect there is a way to think of it as that. Okay, so first I'll talk about what this criterion is. So we'll start from an easy structural assumption, which I said real world graphs, social networks, they have lots of triangles, and I'll translate that into a spectral criterion. So triangles in social networks, what does a triangle in social network do? Mean you're on Facebook. I don't know if people still are on Facebook, but you have two friends on Facebook. Turns out your friends are very likely to be friends. Sorry, the clickers sometimes, yeah. So this is a well-known quantity called transitivity, which measures how many of these wedges are closed. And this thing is 1 if your graph is a union of cliques. And if you just want to take a order any G and P, you'll have to get P to a very high value to be able to get something like where transitivity is constant. On the other hand, if you take a real social network, say Facebook, the reason I picked Facebook is because on Facebook, I think you cannot have more than 5,000 friends, which given that there's like a few billion people, that's a very sparse graph. If you look at Facebook, it has very high transitive closure. Social networks typically have 0.1 to 0.2, this range, which is quite significant, even if it looks small, maybe. If you try to replicate that, you'll see it'll take a fair amount of structure to be able to get there. What we want to do is take this and translate this into a spectral condition. So I'll start with the outset where I say that the ideal dense cluster is a complete graph. So when you look at graph matrices, there's two very popular matrices that come up: the normalized adjacency and the normalized Laplacian. Laplacian is typically better behaved, positive semi-definite. Most people do like the Laplacian more. However, in this talk, we will talk about the normalized adjacency matrix, and you'll see hopefully why we use this one instead. So the eigenvalues here will go from 1 to -1, and this will just be flipped around this, and it goes from 0 to 2. So if you want to find a small cut, you can find this, and the goodness of this cut can be related to the spectrum by what we call the Chiger inequality. And it's a very well-known, I'm sure people here have seen it in some form or the other. And it's an extremely celebrated result and very cool work on that. One of my personal favorite results. And many modern algorithms in real life try to actually get Chiger-like inequalities for different cut quantities. You find some cut and you say that, okay, can I actually relate this cut to some higher order eigenvalue inequality, something like that. There's a lot of work on that. There's always new work coming on it. All of it is very cool. I really like it. But again, there's no spectral condition for the decompositions into these multiple huge number of pieces. That's what we are going to get to. So what does the spectrum of the adjacency matrix look like? So the number of connected components is actually the number of times the eigenvalue 1 appears. So if your graph is a disjoint union of so many cliques, something like this, you'll have 4 ones. Now let me add a little bit of noise on top. Following statement is a little wishy-washy, but you can expect that it'll not move a lot from these 4 ones. So it's not exactly 4 ones. You expect that there's still 4 eigenvalues that are kind of large. This was the basis of us getting to where we were, because we realized that if our graph does have these good clusters, we need to have several large eigenvalues. So before actually bridging these two, I'll give you the metric first. The metric is spectral transitivity, which is if you take the normalized adjacency matrix and you look at its eigenvalues, let me look at the ratio of the trace of the cube and the trace of the square. So any guesses on what this behaves like, or anything? Anyone see? What's an upper bound? Sorry? Yes, pretty much. But it's normalized. So you're right in it could be just number of triangles by number of edges, but it's not exactly that. So because it's the normalized adjacency matrix, it's kind of like a weighted ratio. Turns out this takes values exactly equal to or less than 1. If you have simple graphs, in fact, the maximum you can show that it's if and only if your graph is a complete graph. If you don't have self loops, it's going to be 1 minus 1 over n minus 1. If you add self loops, that can go up to exactly 1. And if your graph is a disjoint union of k cliques, it's going to be some 1 minus some small value or function of k. Yeah, okay. So maybe that's not actually had a slide on that. I removed that, unfortunately. But think of it as essentially if you look at the unnormalized adjacency matrix, what's the trace of the cube going to give you? Think of a single operation, the matrix operation, for the adjacency matrix. What the adjacency matrix tells you is how many ways can you go from I to j. That's the entry in ai comma j. Right? So that's always 1 for some and 0 for cases. Now, if you do 2, that means how many ways can you go from a to j in 2 steps? If you do 3, that's how many 3 paths of length 3. Trace is I comma I, which means exactly how many self-returning 3 paths there are. You can show that that is 6 times the number of triangles. There's an overcounting factor. So what we are getting here is a weighted version of that. Does that answer the question? Yeah, sorry, I had that slide, I just removed it. So the condition I'm telling you is tau of g is going to be theta of 1. What does this mean? Why is this kind of, what does it mean for tau g to be a theta 1? It means that the cube is lower bounded by the square by some constant. What does that mean? So let's actually look at some eigenvalues and let's see what things look like. So this tau is this ratio over here, right? So let's consider one easy case where this eigenvalue, the first one, is exactly 1. So what's the contribution to the numerator and denominator? All 1, right? Perfect, great. Let's consider the case where this is 1 minus x for some small x. What would the square be? Small x. 1 minus 2x, roughly. Next one, 1 minus 3x, right? So the cubes are smaller than the squares because we are in that regime, but this is not too bad. We are losing a little bit, not a lot, right? Now, let me give you a bad case where the eigenvalue is negative. What happens then? So in the denominator, you have a positive term. You're losing something in the numerator, which is bad. You're eating away at things. You want a lower bound and you're eating away at things. Which is why intuitively, because the cubes decay much faster than the squares, we think of this condition as essentially saying that this is eigenvalues which are large. It's not a very rigorous analysis, but I'm hoping the intuition goes through. Does that make sense? Okay. So that gives you the criterion. Criterion is we define spectral transitivity tau for a graph G. When tau is theta of 1, there is a nice decomposition that is internally dense. So far, so good? This reweighting. So I told you that this thing, that was a very good, correct observation. In fact, that is triangles by edges, but there is a reweighting going on because we take the normalization. So what exactly is this reweighting? And for an edge, you say that the weight of the edge is 1 over du dv. For a triangle, it's 1 over du dv dw. So essentially, for each triangle, each edge, you assign some weight. The way I like to think of this, to unpack this reweighting thing, is that this is discouraging low degree vertices from forming triangles with high degree vertices. Why is that? Suppose you take a triangle UVW where U and V have degree, say, 5, and W has degree, say, n over 5. That is a very low weight triangle. So to us, that is a bad triangle, kind of. We like high weight things. So this is essentially saying that if you have low degree vertices, the triangles it forms with high degree vertices are not particularly useful. So you have a complete graph here, and you have this clique of size log n. These vertices over here, they have very high degree. And we say that, okay, everything, all the triangles that these participate in over here, just let's not even care about them. Those are low weight. We don't really want to preserve those things. And then the counter question can be, okay, then it's good for a high degree vertex to form low degree triangles. So what's exactly going on? What's wrong with a triangle where you have two vertices of degree log n, and it's actually benefiting from smaller forming triangles with a low degree vertex? Does anyone see why that is not an issue? We are kind of like, seems to be we're looking at something weird there. Sorry. So okay, sorry, who asked the question? Sorry. So I'll answer the question directly, maybe. So there doesn't seem to be an apparent, there's a penalty for low degree vertices forming triangles with high degree vertices, but there's no penalty for high degree vertices for forming triangles with low degree vertices. If anything, it's actually encouraged. So what's going on, my claim is that these high, low, low triangles are hard to achieve. Actually, it's supposed to be high, high, low. My bad. Will make density hard to achieve. So as an example, let's look at this edge where both endpoints are of degree log n. Assume that, let's assume that all of the neighbors are actually common. So there's log n triangles on this. Right? What's wrong with this situation? Why is this bad, given the context of everything I've said so far? Exactly. We still have this goal in mind. If these degrees are low, you will never form high density in this induced subgraph. Which means that this case, if you also care about internal density, this case will just be discarded by that side. Does that make sense? So turns out reweighting is actually an algorithmic boon. And this was an explicit case that the existing paper failed to solve. So suppose you have a high degree vertex with a lot connected to a lot of distinct communities. Suppose this is Twitter, this is Taylor Swift. I don't know at this point how many followers she has. I don't know, billion, but lots of. So suppose given the old paper, what they tried to do is they wanted to preserve a constant fraction of triangles. Now, suppose you have n over log n communities, and the celebrity is adjacent to everyone in your network. So you can show that essentially most of the triangles are going to be formed with the celebrity. It's not right to actually try to preserve most triangles. The celebrity is not meaningfully part of these communities. Maybe these communities are people from different countries. They don't talk to each other. The celebrity is not part of the fans from that community. Well, they would like it to be, but probably not. So without reweighting, the only way to preserve, in this case, a constant fraction of the triangles with these celebrity vertices is to output the non-dense graphs. So that's a bad metric. However, if you consider the reweighting, these are all low weight triangles, and you can discard these and still preserve a constant fraction of triangle weight. Which is why this reweighting turned out to be a very significant algorithmic boon, because it told us that the right metric to look at is this. Also, it turned out to be a very nice mathematical hammer because it gave us a combinatorial algorithm and actually related that to the spectrum. Now, how does it do that? If we take this tau, you can show that with that weighting scheme that I had earlier, this is essentially a ratio of triangle weights over edge weights. So I can connect the spectrum of the graph to a combinatorial algorithm. I don't need to do any Rayleigh quotient type of stuff, but this just goes through. And this holds exactly through the same step-based random walk thing I was saying in matrix multiplication thing, except the steps are now weighted. So reweighting, again, the scheme is just very simple. Pros is that it's almost magical in some sense. At least to me, when I first saw this, I was like, oh, this solves so many issues. It gets rid of the algorithmic challenges and at the same time gets us a very nice connection to the existing well-studied algebraic objects. The cons, unfortunately, is that by doing this, first of all, these third power things that we mentioned, they cannot be shown as a norm. We tried some variants. We don't have a result. Maybe someone here can. Please let me know. I'm very interested in seeing that. It also needs our calculations to be a lot more careful. Earlier, you could just say, oh, yeah, something holds. We need to be careful with the weighting. Each triangle needs to be considered differently because of degree and so on. So that gives me hopefully, that tells you what our nice decomposition is. We no longer want to preserve a constant fraction of these triangles or edges. We want to preserve a constant fraction of the weights. Does that make sense? Any questions? Okay, I have 10 minutes. Okay, last thing, what is this goodness metric? I like to think of edge density as necessary and insufficient. If you take a clique, every subgraph of the clique is a clique. Which of these cliques is better by edge density? Degenerate. I'll throw a definition at you and then I'll unpack this. What I call this definition is uniformity. For a given matrix M, a submatrix S of size K is considered to be P uniform if a P fraction of the off-diagonal entries are in this range, P over K, comma K over P. Okay, that's actually, okay, there's an error here. I don't know how I didn't catch this for so long. But this should be P over K, comma 1 over PK. Sorry. So unfortunately, I can't change these on the slides right now, but that is the correct metric. So first of all, I think everyone can see this, which is this already gives us edge density of P. Does everyone see that? Constant fraction of the off-diagonal entries are non-zero. You have edge density if you consider M to be the normalized adjacency matrix, right? So it supersedes edge density. And you can also define this notion of strong uniformity corresponding to that triangle density metric. I'm not going to go into the details of that. You can see the paper for that, but it's not very important right now. I'm telling you, like, take my word for it, there's a way to do this for triangles. But what more is uniformity buying you? Uniformity implies edge density P, and also it tells you that endpoints of each edge of that P edge density must have degree close to the size of the subgraph. So let's take this clique. This is perfectly uniform, right? In the normalized adjacency matrix. Suppose this clique exists around this. What are the corresponding entries in the normalized adjacency matrix? It's going to be 1 over log n, right? Because it's the degree. This is going to violate your lower bound on the entries because your entry can only be 1 over 6, right? So what this is telling you is that, well, yeah, if you enforce this for vertex, you get triangle density. But what this is telling you is that this is not the right community. Because yeah, there is perfect density, but the density is formed by vertices which would benefit from being in a much larger community. Does that make sense? So, and given the figure, I hope people agree with that, which is like, yes, this is a clique, but this probably belongs to this community if that's dense in there, right? Do people agree with that? Moreover, what you get is that if you have uniform subgraphs, they have Frobenius now induced of theta of 1, and also strong uniformity implies triangle weight of each piece is also theta of 1. So the density condition is therefore that each piece is going to be strongly uniform. Okay, now I have unpacked all the things, so let me give you the full theorem. So the full theorem is what we call the spectral triadic decomposition. If tau of a graph G is theta of 1, then there exist clusters in a graph such that the mass of the graph is contained inside these clusters. What is the mass? The constant fraction of the Frobenius norm and the triangle weights. Each cluster is strongly uniform. We can also show that, or not we can show, we actually give an algorithm to find these clusters, and in that algorithm, the output is going to be radius at most 2. And there's poly tau hidden inside the constants, basically. So that's why we need tau to be theta of 1. So everywhere you see a theta, put a poly tau somewhere, and that's why that bound is required. Why I think of this as a new spectral theorem, because Cheeger tells us that when the spectral gap is low, your graph can be cut in 2 pieces using a low conductance cut. What we tell you is that when spectral transitivity high, your graph will decompose naturally into many pieces. Finally, last 5 minutes, let's actually give you the algorithm. So should probably change the slide name. I don't know. We've called the procedure a cleaning procedure. For an edge E, you consider the triangle weight incident on the edge. You clean away the edge if the triangle weight on the edge is less than a constant fraction of the weight of the edge. What this is essentially doing is, so C is this density parameter, which is the sole parameter we require for our algorithm. You can just, it's a kind of a density regime that you say that, okay, we want so many dense things, so the density to be so much, and so on. So what this means is that in this case, this doesn't form any triangles, right? So what happens to this edge? Gets removed from your graph. What if I do this? Will this edge survive? There's some triangles on there. It will still not survive because this is high degree. Therefore, the triangle weight is low, which means this is not enough. This cleaning procedure kind of implicitly gets you this uniformity-like condition on your neighborhood. Question is there at all something in your graph? We can show that if we have tau equal to 1, then cleaning will not destroy everything. There'll still be a lot of stuff left in your graph after cleaning. What it does actually enforce is that surviving edges of high participation in triangles. I like to think of this as a kind of a sparsification procedure that takes this global tau thing and translates it into a more strong local condition. So far, so good. Now that we've done this, we can actually extract it as subgraph. So what we do here is we pick a vertex with lowest degree in your graph. You look at its low degree neighborhood. So you look at vertices with roughly the similar-ish degree. Then you look at the 2-hop neighborhood. And you say that essentially you look at how many triangles these vertices in the 2-hop contribute to your low density neighborhood. So there's like an ordering. Let me actually say that this is the highest and I go down like this. The decreasing contribution to your cluster. I go like this, and at some point you'll see that you'll get a vertex which contributes more outside than inside. Stop there. The trick here is that we have a slightly slick inequality that shows that you can achieve this using just the D order of D vertices, where D is the degree of the graph. You don't need a lot of vertices. That's how we get the size bound. Final decomposition procedure can be summarized as you have an input graph, take the cleaner, take a cleaned graph from the cleaner, you put it through the extractor, and the extractor outputs one dense piece, and you keep doing this till there's nothing left, and that is the collection of your dense subgraphs. Algorithm makes sense? Here? Okay, great. So it's an interlaced cleaning and extract, you can see here. So I started this whole thing with this feel like I want things that work well in practice. What does it do in practice? These are on citation networks, condensed matter physics. These are people. You can look these people up. Some people might know this guy, Wolfgang Ketterle. He used to work on bosines and condensates, and I think he won a Nobel Prize. A bunch of these are his students, others are his collaborators. These are actually people who do work together. These are actual fairly well-formed communities. And the nice thing I think we found, which is not there in this figure, is that to go a little bit further, you start getting fewer and fewer people who actually meaningfully work with these people. This is for people who work on fullerene and graphene kind of stuff. Again, where's the person name? Smalley. Does anyone here know Smalley? He was one of the pioneers in this. He made some graphene. I think I forgot exactly what he did, but these are people who work all on these materials kinds of things in physics. They all do the same kind of stuff. Okay, this is perhaps more understandable to us. This is from DBLP, co-authorship networks. These are all error correcting papers. Look at these. These are all logic database recursive program papers from, I think, Sigmod. Well, largely Sigmod, that kind of venues. We have, again, to reiterate, we got thousands of clusters like this from a single graph. I cannot show you summarized statistics for that, but I can give you the output. You can look at it yourself. This is not there in the final paper, but this is also very interesting to me. These are protein interaction networks. These are PPI networks from, left one is from E. coli, right one is from Streptococcus. And these are a protein complex, I shouldn't call it a protein complex. These are a group of proteins which largely have roles related to aerobic respiration in E. coli. Again, your graph doesn't know any of this. Your graph is looking at some topological structure and giving you something. To me, it's very interesting that you can do all of that and still get like close to functional units. Like if you actually know nothing about your graph, I think this is a very useful way to actually do some knowledge discovery on things you don't know. And I said robustness. How much time do I have? Okay, so yeah, 12:05. Okay, I'm going to skip this part. Essentially, what we show here is that if you add a little bit of noise, our results are still stable, but things fall apart very quickly in a bunch of other methods. Like these will just not give you sensible outputs. And here's the spectral cut algorithm. I remember there was a question on that. When it knows exactly how many pieces are there, it gives you great outputs, but you remove that and it's just nothing. The second paper does something which we call a recovery algorithm. Like so far, I've told you there is a decomposition, there exists these dense pieces. With a little bit of modification and some slightly stronger guarantees and a little bit more care, we can show that if there exist these uniform-like pieces in your graph, you can also recover them. And if the clusters are actually well separated, which is the case that Shiger and all do, we can actually get near perfect inequality recovery. And in real-world networks, we did this on some real-world networks. There was a use case for this. We saw that if you added heuristics to add like unassigned vertices. Oh, I didn't mention this, sorry. This is not a strict partition in the sense like not every vertex could be in a dense cluster. There's a bunch of vertices which do not meaningfully participate in communities, which I think is very true in real-world noisy graphs. Those will be output as unassigned singleton vertices. You can actually assign them to some things using some heuristics, which we do in the second paper. Code is here. Please feel free to download it, use it, tell me what it looks like. And this is the actual density quality from the out. output. 0.8. So anyway, so I'm out of time. Some ongoing work, overlapping clusters, which was a question you asked me. We have half of the stuff there. Few months, I'll let you know if we get there. Insight into behavior of tau, which is a question I really, really care about. It's a funky quantity. Not completely sure what it looks like. I would love to see what it looks like. Anyone here has some insight, please. Is there a theory for directed graphs? Spectral graph theory typically doesn't translate well into directed graphs. We're trying to look at this. Not completely sure, but again, stuff we are doing. And are the higher powers of eigenvalues useful? Like we looked at powers cubes. Maybe you can go up to some more. Maybe it stops at log n. Maybe beyond log n there's no value. These are questions. These two especially are questions I think I am personally very interested in. If you have thoughts, please let me know. Okay, I think I'm already over time, so thank you, and I'm happy to take questions.
Questions? So, how many communities do you usually get?
Beginning hundreds of thousands even for large enough graphs. Typically, for what happens in these large networks, at least, is that a lot of these vertices are quite noisy. They do not meaningfully participate in the community. So a lot of them end up being singletons. The more you modify the heuristic I mentioned at the end, the closer you get away from that. But yeah. Typically, you can get like at least tens of thousands and million vertex graphs is quite easy. I think the modularity thing is quite common, which is the resolution limit, which is there seems to be a high propensity for outputting large pieces. Not sure how well understood it is. I have a few questions I do not entirely have the answers to, but that is a fair. And typically, I think like the overlapping community thing is actually something that is not particularly well understood. There's some work, but it's not nearly as well understood as the other ones. But honestly, the Leuven algorithm is something I personally like a lot. Works very well in practice, but it does one thing, which is it actually gives you disconnected pieces. Because it does what it does is it does this heuristic. There's no actual proof for the correctness there, but it does this heuristic where it locally maximizes modularity. So essentially, it changes changes edges and vertices in versus out community. It basically starts with an assignment and then adds a vertex to that, sees if that increases modularity and so on, and does this till some sort of convergence. And this can often lead to like locally disconnected pieces. And it's quite common actually. There's a paper that's follow up to that called the Leiden algorithm. It's from 2019 or 18, I think, which gets over that. But there's a bunch of other issues with these real world community detection methods. Some we do solve, some we don't.
Thank you, speaker.
Thank you.
Here's something from CSET.
Thank you.
I think it's a t-shirt.
Okay.
Thank you.
Okay. Will you stop sharing?